Hello friends, welcome back to the tetrahedron chemistry classes. So in the organic spectroscopy previous year question series, today I am going to discuss the questions which have been asked in the CSIR NET 2016 examination. Okay, so this lecture will include both the sessions, right? We will discuss the June 2016 questions as well as December 2016 questions. Okay, so without wasting the time, let's straight go to the question. So my first question, as you can see here, but it says that this question has been asked in the June 2016 examination, and it says that among the following, the compound that displays an IR band at 2150 centimeter inverse. That means you have been given these four compounds, and out of these four compounds you have to select which compound will give you a band which at 2150 centimeters. So let's investigate how we can solve this particular problem. However guys, this problem is based on your memory. If you have memorized the certain absorption frequencies or stretching frequencies for the compounds, only then you will be able to solve this type of the compound, right? So as you can see, this is your nitrogen double bond nitrogen, and here see phenyl is there, and another phenyl is there, and here it would be a lone pair, so it is a kind of symmetric thing. So there is no question of IR absorption, especially when you consider nitrogen double bond nitrogen. So you can discard this one, and you know this pH is the phenyl actually. Okay, and when you have this phenyl ring, then for this phenyl ring, you know the carbon stretching, carbon double bond carbon stretching, it's resonate around 1600 centimeter inverse, right? And it goes up to 1475 centimeter inverse. Okay, so this cannot be your answer, because in the options you have been given only this 2150 centimeter inverse. Now this is another compound which is the interesting one, and in this compound also you can see this is carbon double bond carbon, and that carbon double bond carbon, especially when it is of alkene kind, it absorbs the radiation frequencies or gives the stretching frequencies somewhere around 1600 to 1618 centimeter inverse. Okay, and this part is basically the ester part. This is carbon double bond oxygen, and this is single bond, then your Me. So if you see this carbon single bond oxygen, then you know carbon single bond oxygen would resonate somewhere around, see this I can written here 1100 centimeter inverse, and it can extend up to 1300. So this cannot be your answer. And ester carbonyl functionality, if ester carbonyl group is there, then it would have certain different frequencies, not this 2150. So this option you can again discard. Okay, now moving to the moving to the third problem. This could be your probable answer, right? How? This is your benzene ring. Okay, and it is actually kind of this thing, nitrogen double bond nitrogen, and again nitrogen double bond nitrogen. Okay, so this would be positively charged because it is tetravalent, so it must lose the electron pair, and this is divalent, so it should have negative charge or the negative due to this lone pair. Okay, and this is actually the resonance structure of this species. So what I can do, I can make some space, so I can discard this, and the structure actually you have been given in that manner. Okay, this was your benzene ring, right? And this is in resonance with this one. See what can happen actually in that case, right? This lone pair can come here, fine. So this would be now triply bonded. Okay, and this will come here. So your structure would be like that. This nitrogen would be negatively charged, and then this is nitrogen again, and that nitrogen triple bond nitrogen. Of course this is positive. So this is, you see, nitrogen triple bond nitrogen, it actually absorbs somewhere around 2150 centimeter inverse. So this option C is looking the correct options, right? And if you check, if you go for the option D, see option D is again a problematic here, because this carbonyl functionality which is given here, it will resonate around somewhere 1820 to 1660 centimeter inverse. This cannot be your answer. And this nitrogen single bond hydrogen, which is this one, it resonates around this 3400 centimeter inverse, right? So you can see that this question is based on your memory actually. If you have memorized the concepts, if you have memorized the certain staging frequencies, and you have memorized some of the concept as resonance I have shown you here, only then you will be able to solve this particular question. Okay, now moving to the next question, what it says. Okay, it is again you can see the June 2016 examination question. In the proton NMR spectrum of Martinel, right? This compound is actually your Martinel compound, and it is a common component of the essential oils, right? When you do the essential oil chemistry, then you will find this compound there. Okay, so the two methyl groups, the question is talking about this methyl group and about this methyl group. These two methyl groups are expected to display signals at chemical shift values in the ppm. Okay, that means these two methyl groups are given, and you have to tell that what would be the chemical shift of these two methyl groups, right? So if you recall my last lecture where I have discussed alpha pinene structure. Okay, see the same question actually in the previous year examination, like say I think in the 2015 or 14, they asked actually the same question based on the same concept actually, alpha pinene, where they have asked the chemical shift. Again they are asking the same question. So I am telling you, right, these two methyl groups, right, these two methyl groups which are shown here, due to the magnetic anisotropy in NMR spectroscopy, you know the magnetic anisotropy is there due to presence of this double bond alkene part. So these two actually, you see, they are not equivalent. These two hydrogens are not equivalent. You can simply think in that manner. This is the double bond, and this methyl is close to this one, right? When it is there close here, so it could be your shielded one, right? And it is your de-shielded one. So shielded one will have the higher chemical shift, and the shielded one will have the lower ppm value in the chemical shift, and de-shielded one will have the higher chemical shift in the ppm value. So these two are not equivalent. So when these two are not equivalent, so what you can do, you can immediately discard this option D, because this option D says that we will get the signal of 6 hydrogens and we will get the singlet for this one at 7.0. But I told you this and this, they are the different ones, so they cannot give you the one signal. Based on the same concept, you can also discard the option C. Option C also says that this will give you the peak at 1.22 and it will give you a singlet again and 6H. So these two can be discarded. So either A or B, out of these two, anyone could be correct, right? So, and again you see, if I draw the structure again, right, if I draw the structure again for this one, say, however, it is not always very easy to draw such kind of the structure. For this you have to do lot of practice of drawing these kind of the structures. Okay, so this is this one, and you see, if I continue this bond here, right, this is this peak. Okay, and this is the double bond which is here, and this is your aldehyde functionality, right, and this is your methyl and this is your methyl, right? This is CH3 and this is again CH3. So you know, when you study the NMR spectroscopy, so there would be current like that, right? There is the magnetic field, right, generated by these electrons. So you can see this methyl actually, right? This methyl is you can see this is slightly shielded one. It is shielded methyl. When it is shielded methyl, so it will have lower ppm chemical shift. Please remember. And this is the de-shielded. When it is the de-shielded one, so it will have higher ppm chemical shift, right? And now in the two options, see 1.35 and 5.0, 0.74 and 1.33. So you might get confused actually, right? So this is shielded, this should have the lower value of the ppm. So this 0.74 is lower here in this option because 1.33 is bigger, And in the option A also 1.35 is actually the lower value compared to this 5.0. But please remember, these are the methyl protons, and you know methyl protons in the NMR spectroscopy, these methyl protons resonates at very low field. Please remember, not low field, sorry, we cannot say the low field, we can say the low ppm value. Okay, we can say the low ppm value. But you can see here, in that case it is showing that the 5.0 ppm, it is not possible for the methyl proton to resonate at 5.0 ppm, right? That much of higher chemical shift cannot be possible for the aliphatic proton. So you can discard option A also. So what you left with the option B. So in that case your option B is looking the correct answer, where 0.74 is the chemical shift of this one, 0.74 ppm, and for this one we are having 1.33 ppm. Okay, because 3 methyls are there, so these are the 3 hydrogens, and this is a singlet because it is giving only 1 peak. On the same basis you see the 3 protons which are this one, right, and singlet. So this question is again a very easy question, only if you know the concept of the magnetic anisotropy. Otherwise it would be difficult to solve such kind of the questions. You have to have the little idea about the natural products also. Okay, now moving to the next problem, what it says. Right, this question you can see here what it says. In the UV visible absorption spectroscopy of alpha beta unsaturated carbonyl compounds with increasing solvent polarity. So this is my way of writing increasing, arrow is up and SING, which shows the increasing. Otherwise you can write also increasing, right? And this is the solvent polarity. When the polarity increases, then lots of things happens in the UV visible spectroscopy. I have made an exclusive lecture on the solvent concept of the solvent in the UV visible spectroscopy, right? If you haven't watched that particular video, so here at the right top you can see the link, right? You can learn the concept there, because the question, the concept which I am going to explain to solve this particular question, I have already explained in my previous lecture. So that lecture would be very, very beneficial for you, right? So first of all, see, don't go in the don't look for the options actually, right? What you can do, you can straightforward draw the alpha beta unsaturated carbonyl compound. So this is my carbonyl functionality, and say this is one, and what I can do, so this is my alpha carbon, this is my beta carbon, so I can put a double bond here. So at alpha position, you can see here at alpha position and beta position, I am having the unsaturation, that is the multiple bond, presence of the multiple bond, and this is your carbonyl functionality, right? And remember, when you draw this one, then this oxygen will have a lone pair. So basically very important fundamental transitions for alpha beta unsaturated carbonyl compounds are like that. First is where non-bonding electron can be excited to the pi anti-bonding level. Okay, this is the transition, and that transition actually gives you the lambda max value somewhere around 280 to 290 nanometer. Again you have to memorize these things, okay? But this transition is forbidden because its molar absorptivity or molar absorption coefficient or molar extinction coefficient is very low, which is actually the 15 only. So this transition is forbidden. But nonetheless, this transition is very important in identifying this particular compound, these types of the compounds, okay? And then the second transition is kind like that, pi bonding electrons can be excited to the pi anti-bonding, okay? So that means these electrons can be excited to the pi anti-bonding, right? And these electrons are also can be excited to the pi anti-bonding levels, okay? First of all, you have to understand these things. Now a very important concept which you must remember in solving this this question, the structure of the compound in the excited state and in the ground state. You should know this thing, okay? So how we can explain this one? See, for example, say, right, so here in that case, this is my alpha beta unsaturated carbonyl compound, okay? This I am writing as the ground state, okay? and when the electronic excitation takes place, right, on the absorption of the light, then you will have your excited state. And in the excited state, what can happen? The electron will go up, this is negative, and this carbonyl is positive. So in that case, you see this is your excited state, ES I am writing for the excited state. So in that case, you can see in the excited state, polarity of excited state is very high, because there is clear formation of the positive and the negative end here. Okay, so in that case, here your excited state is more polar. Okay, and in the question itself, if you go back in the question itself, what it says that in the UV visible spectrum of alpha beta unsaturated carbonyl compounds with increasing solvent polarity, that means you are increasing the polarity of the solvent, right? So when you increase the polarity of the solvent, what can happen? Here say I am writing polar solvent. Okay, polar solvent. So what can happen? There would be the interaction between this polar excited state and solvent polarity, like hydrogen bonding. And what can happen? That hydrogen bonding actually stabilize the excited state more, and when this stabilizes, its energy goes down. So how in the picture we can depict this thing? Say this is my pi bonding level, and this is my pi anti-bonding level. Okay, and I am talking about the transition which is the allowed one, which is pi bonding to pi anti-bonding, right? This I have written, I think, in the last page. Okay, I have missed this transition. I should give the value of this transition also to you. Very sorry for this one. This actually gives you the lambda max value somewhere around 188 nanometer, and for this epsilon max is actually 900. Okay, and this transition is the allowed transition, please remember. Okay, now if I come back again to the same problem, so this is my allowed transition, this one my allowed transition, and here what you can do, this is the energy gap. Delta E. Okay, and what can happen here? Less polar solvent I can write, less polar solvent or non-polar solvent I can write. Okay, and here in that case I have increased the polarity of the solvent. That means I have added a solvent which is more polar than the previous one. So what can happen? You know, this excited state, it is more polar. Okay, and what can happen? It's this excited, that this particular solvent, this polar solvent, will stabilize that excited state, right, more than the ground state. So what would be the change in the change in the energy levels in that case? So the change in the energy level would be like that. See, this will come here. Okay, and this will come here, right? In that case you can write. So you see, this is the stabilization of this excited state, and this is the stabilization of the ground state. You can clearly see in the picture this decrease is more compared to this decrease, right? So in that case you can see here, this is the energy difference. Okay, that mean in that case delta E decreases when delta E decreases, and you know E equals to Hc by lambda. E equals to Hc by lambda. So when E increases, lambda increases. So here in that case lambda increases. Lambda increases means, if you think like in that manner, Vi B G Y O R Vibgyor. So this will have high wavelength. Okay, and sorry for my bad handwriting. What I can do, I can write it again and again. So this is the problem with me. So I can write high lambda. For this I can write low lambda, right? And so what can happen in that case? If we are adding the polar solvent, increasing the solvent of the polarity, then the transition which is pi bonding to pi anti-bonding transition, this transition pi bonding to pi anti-bonding transition, it undergoes red shift. ठीक है. And this red shift, you know, if you see the what is the red shift is basically your bathochromic shift. If I go back, so please check what the option shares here. Pi bonding and pi antibond, pi bonding to pi antibonding undergoes the bathochromic shift. Yes, we have seen this can happen. And non-bonding to pi antibonding undergoes the bathochromic shift, and pi bonding to pi antibonding undergoes hypsochromic shift. This is not possible. So what you can do, you can immediately discard the option B. Both undergoes bathochromic shift. No, it is not possible. Both undergoes hypsochromic shift. It is not possible. So what you left with the option A only. So automatically you can see, without going into the further solution of the problem, you can immediately say the option A is looking the correct option. But if you want to know how actually this happens for the non-bonding transition, so I am telling you, in the non-bonding transition, if you check this one, non-bonding transition, in that case ground state is more polar. So if you increase the solvent polarity, well, what can happen? So ground state energy will decreases more than the excited state. Okay, so this will obviously undergo the your hypsochromic shift. Okay, but I have explained very clearly for this one. So if you want to learn this question is in pretty much detail, you have to see my lecture on the solvent polarity. I hope this makes the sense and this is good for you. See, if you want to learn these things further, you can consult or you can refer your Pavia Lempman book, which is a very good book. Okay, so now moving to the next problem, what it says. So guys, you can see my next problem, which is again from the June 2016 examination. What it says: a compound displays the following spectral data. That means in that case you have been given the different spectroscopic data. Okay, first you see the IR spectroscopy, which is showing that the signal at the 1619 ppm, right? And you know the signal around 1700 ppm is due to the carbonyl group. So obviously you should remember this point. This actually shows the presence of the carbonyl group. So you have to select the structure where you have been given the carbonyl group. Okay, but in that case you can see this is the carbonyl group, this is carbonyl group, this is again the carbonyl. In all the options we have been given the carbonyl group. So this is little tricky now. So let's see how we can solve this problem. Okay, so based on the IR spectroscopy, I am giving you a simple way, right? Say for example, before going into the details of the IR, what we can do, we can discuss another thing. Yes, we can see the 13C NMR. 13C NMR is showing the signal at 197 ppm. This is the value which will give you the idea what is this actually. Please remember, when you have the carbonyl group, right? This carbonyl group present in the compound, and it is giving you the peak somewhere around 200 ppm. Okay, and you know this 219 not p, very sorry, not ppm. Yes, ppm. Yes, ppm. Okay, this is NMR. Okay, so it is very close to actually 197 ppm. So this is actually the carbonyl group of the ketone. Please remember, whenever you have the when you have been given the data of the carbon NMR and you have been given the signal at 197 ppm and you have been given the carbonyl compound, so it blindly you can mark it as the presence of the ketone, right? If carbonyl group is from the ester moiety, right, then it would have the different chemical shift, right? For ester moiety, it will give you the signal somewhere around 170 ppm. That means ester is not there in that case, but ketone is there in that case. So you see options. First option is the ketone. Yes, this is the probable answer. Second option is the ester. This option is not possible because this ester cannot give you the signal at around 200 ppm. So what you can do, you can immediately discard this. This cannot be your answer. Okay, And again you third option, yes, this third option could be your answer because this is the ketone. And after that you see this is the ester, so this cannot be your answer, right? So this is double bond, this is the ester moiety. Okay, so option D and option B, these two can be immediately discarded. So when we are discarding these two options, so what I can do, I can remove them. I need some space to solve the problems furthermore. Okay, now you left with this one. Now here in that case you see this 1690 is not very important, right? This is the carbonyl, this is carbonyl, right, which is quite good. It is suggesting that your carbonyl group is there, but it is not actually giving you the very clear idea. But again, see, 1700 means ketone. Now the correct idea would be there when you see the proton NMR spectrum. So what the proton NMR spectrum says that, see, if you have done the spin systems of the your spin systems study of your substituted benzene ring, then you will be able to solve this question. Pretty straightforward. So here you see what we are getting at 6.9, doublet of 2 proton. Okay, and at 7.8 again we are getting doublet of 2 proton. So mark my words, remember my words, and mug out my words. Whenever you have been given these two options, 2 proton doublet and 2 proton doublet, that means 2 signals of 2 proton doublet, then it shows para substitution. It shows para di substitution. It shows the para di substitution, right? And you know this compound is, you see, if this is if this is the principal functionality, so this is ortho position, this is meta position. Okay, when these two this is meta position and this is ortho, this is meta, this is para. So this cannot be your answer. You can immediately discard option C also. So what you left with the option A, automatically your option A is the correct option. Guys, please remember one thing, there are various ways to solve or to approach the problem. I am explaining you the problem which actually I feel the most time saving trick, or my concept is most time saving. Yeah, I think that my concept, my explanation saves times more. But however, you can go by the another techniques also. So if you know, if you solve this one, then you immediately you can mark this one. But if you want to learn the spectroscopy in detail, then you can, okay, of course you can go further. So how we can go further? This is your CH3, okay, and what I can do, again I can write here OM. This is again CH3. Okay, so this will give you a singlet, and that singlet should correspond to the 3 proton, and this will again give you what? Singlet that should correspond to the 3H. So we should have in the question 2 3 proton singlets. You see, this is 3 proton singlet at 2.5 ppm. This is 3 proton singlet at 3.8 ppm. Now you have to decide which one is which. So here you can see in that case, this methyl group is directly linked with the oxygen, which is highly electronegative. So it causes the de-shielding. When the de-shielding occurs, then the your signal goes the downfield. Downfield signal means higher ppm value. So this signal would resonate around 3.8 ppm. Okay, there is no problem in that. Of course, this would be upfield, that means 2.5 ppm. This is one way, right? And now you see, this is the hydrogen again, and this is the hydrogen again, this is the hydrogen again, this is the hydrogen again. Okay, and if you know, see, if you mark them, say this is my hydrogen of one kind, and this is again the hydrogen of one kind, because their environment are same. And this is hydrogen of second kind, this is hydrogen of second kind. Why I am saying this? these two hydrogens are in the vicinity of this carbonyl, while these two hydrogens are in the vicinity of this one, right? So what can you can see, this hydrogen and this hydrogen is different, this hydrogen and this hydrogen is also different. So what can happen, it can couple with this one, it will give you the doublet, and this will couple with this one, this will again give you the doublet. So that's why we are having the two doublets, one at 7.8 and another at 6.9, right? So it is up to you whether you explain for these two or these two, right? But remember, this doublet is due to this hydrogen and this doublet is due to this hydrogen. Since these two are the same kind, so they will appear at the same chemical shift. Okay, and now you have to decide which one is which, right? So in that case, you see the electrons pair are there, okay, and these electron pair can participate in the resonance, right? So this hydrogen is basically, H1 is more shielded, it is more shielded, okay, and when this hydrogen is more shielded, so it is actually what can happen, it will have the higher, it is have the higher value of the ppm, okay, and this is actually not that shielded. So this hydrogen, which is H1, this will give you the signal at 7.8 ppm, this will give you the signal at 6.9 ppm. So this is how you can go for these kinds of the problems. However, you can apply your own knowledge and you can solve the questions by your own also, but I am telling you the way in which you can save your time in the CSIR net and in the gate examination, okay. However, there are various ways to approach the problem, okay. Now moving to the next one, what it says, okay, again the problem from the June 2016. In an NMR spectrometer containing a 2.5 Tesla magnet, Larmor frequency of the proton is 100 megahertz. The radio frequency used in this spectrometer has an associated magnetic field strength of 2.5 into 10 to the power minus 4 Tesla. The duration of a 90-degree pulse. However, see guys, this question is not a very easy question. Generally, see, the guys which you have studied, which get the education from the say state university or from not the very good university, these parts, this physical spectroscopy part, they generally escape actually, right? So for this you have to go for the NPTEL lectures, or you can go for a different YouTube lectures to understand this kind of the problem. But I am telling you how we can solve this problem. A very simple way I am giving you. First of all, you should know how we can calculate the pulse duration, okay. So I am writing pulse duration. So for the pulse duration, we are having the formula, which is nothing but 1/4 multiplied by frequency of the associated magnetic field. Frequency of associated magnetic field. And in the question, you see, you are having the associated magnetic field, but its frequency is not there. So your first job is what? To calculate the frequency associated with the magnetic field. Frequency of the associated magnetic field. So how we can go for this one? Say I am explaining in that manner. Say this is my external magnetic field, which is going like that, okay, and that external magnetic field is having the associated frequency, or Larmor frequency, I can say that 100 megahertz, okay. And now when you have this magnetic field, and in the question itself it is given that in the 2.5 Tesla magnet, Larmor frequency is given, right, for this magnet, right, it is of 2.5 Tesla, and for I can write 2.5 Tesla also here, right, 2.5 Tesla, okay. For this 2.5 Tesla, that is B0, mu0 is actually this one, mu0 is the Larmor frequency, and the radio frequency used in this spectrometer has an, whatever the radio frequency you will use for this spectrometer, that radio frequency will have the associated magnetic field, and that associative magnetic field always goes the right angles to the previous one. So this is the associated magnetic field which is associated with the radio frequency waves, right, and this I am calling as B1, right, magnetic field, and that associated magnetic field is having this much of strength, which is your 2.5 into 10 raised the power minus 4 Tesla. But the frequency nu1 is not given. So first of all you have to calculate this nu1. So how you can calculate the nu1? You know the formula of nu1. Here I can write nu equals to gamma B0 divided by 2 pi. This is the famous equation, famous Larmor equation. Okay, and when you have been given this one, so you can immediately form other two equations. Nu0 for the first one, gamma, which is the gyromagnetic ratio, B0 is B0, and 2 pi. Say this is your equation number 1. Okay, and then for the associated magnetic field, that means for this one, right, for this one I have written the equation here, and for this one I am going to the equation here. Okay, gamma would be constant because both are the protons, and magnetic field is B1 in that case. 2 pi is this one, right? This is the equation number 2. What we can do, we can divide the equation 1 by equation 2. Okay, so what we can do, so in the next page I can write equation 1 divided by equation 2. Okay, so immediately I can write nu0 divided by nu1, that is equals to gamma into B0 divided by 2 pi. Again, sorry for my bad handwriting, gamma B1 divided by 2 pi. Okay, so what can happen? These two can cancel and gamma will cancel out. So what you left with is B0 divided by B1, which simply says that which simply explains the concept of the NMR spectroscopy. Magnetic field is directly proportional to the Larmor frequency. This is the concept. Now you have been given data. Nu0 you have been given in the previous question. You see in the previous page I can see nu0 is what here 100 megahertz and 2.5 Tesla is the B0, right? So immediately what we can do, we can put those value here. Nu0 is 100 megahertz, I can write here, divided by nu1 I have to calculate because associated frequency of the associated magnetic field is not given. B0 I already told you it is given 2.5 Tesla, and B1 is given 2.5 into 10 is the power minus 4 Tesla. Okay, so what can happen? From 2.5 we can cancel out, Tesla will cancel out Tesla. Okay, and what you left with actually nu1 equals to 100 divided by 10 is the power minus 4. Okay, so how it happens actually? See, if you are the biology student and you don't have you are not practicing the basic mathematics, then this step, even this step would be difficult for you. So this is 100 megahertz divided by nu1 equals to 10 raised the power 4, right? So what actually I did, I transfer this 10 is the power minus 4 from denominator to the numerator. So power will change from negative to the positive. That's why it is here. Okay. Now if you bring that nu1 here, then this 10 is the power 4 will come down. So this will you will have this thing actually. Okay. And now if you solve this one, so 10 is the power 2 for this 100, and this will go up. This is 10 is the power minus 4. Okay, and then you will have 10 is the power minus 2. You left with the 10 is the power minus 2. Okay, megahertz. 10 is the power minus 4 megahertz. Okay, now this is in the megahertz, and you see you have to convert this into the hertz. So what you do, 10 raised the power minus 2, you will multiply this value with the 10 raised the power 10 raised the power 6. So please remember, when you know the 1 megahertz equals to 10 raised the power 6 megahertz, sorry 6 hertz. 1 megahertz equals to 10 raised the power 6 hertz. Okay, so this will give you the 10 raised the power 4 hertz. Okay, so if I go back, so I can write it as hertz, SZ. So now what I can do, I can solve this problem here. 1 by 4 is given, okay, multiplied by 1 by 10 raised to the power 4. Ten raised to the power 4. So it is like that, 0.25 into 10 raised to the power minus 4. See, you divide this 1 by 4, you will get 0.25, and bring that 10 raised to the power 4 from denominator to the numerator, it will give you the 10 raised to the power minus 4. So this would be 2.5, or rather 2.5, you can, what you can do, you can write 25 into 10 raised to the power minus 6, okay, because we have to calculate the duration would be in the second actually, right? That's why I have converted that into hertz actually. Without converting this value into the hertz, you cannot get the answer in the second. So 10 raised to the power 25 into 10 raised to the power minus 6 is the correct answer. So option A actually is looking the more correct answer. Okay, I hope you understand the problem, or you understood the problem. Okay, now my next problem, what it says that, my next problem says that Proton NMR spectrum of a mixture of benzene and acetonitrile shows two singlets of the two equal integration, the molar ratio. See, again in the 2000, I think in the 2014 or 15 examination, I have solved this kind of the problem. This is a very easy, straightforward problem, but you should know, you should remember the formula of the acetonitrile. Okay, so this is your benzene, which is C6H6, and this is your acetonitrile, which is your methyl cyanide. Nothing. Okay, so this is having 6 hydrogens and this is having 3 hydrogens. So its integration would be 6 and its integration would be 3. That means the intensity of the peak would be in the ratio of 6 into 3, or what you can do, you can write 2:1. This should be the ratio, but question itself itself says that the ratio is 1:1. So if you want to make this ratio into 1:1, you have to multiply this one with 2. Only then you will have the ratio of the 2:2, that is 1:1. Okay, that means molar ratio of acetonitrile would be 2 and molar and benzene would be 1. So it should be your 1:2. Answer should be 1:2, and option C is saying that it is 1:2. So this is how you can solve the problem. Okay, very quickly I have solved this problem because I have solved this kind of a problem in my previous lecture actually. If you don't understand here pretty much, you can go back, or you can watch this explanation again. Okay, this is very simple and straightforward problem. Now moving to the next problem, what it says that the compound which shows the IR frequencies at both 3314 and 2126 centimeter inverse. See guys, again this problem is based on the memory, right? It is a memory based problem. How you can solve this one? Please remember, when you have this CH3, then your carbon hydrogen stretching frequency would resonate around 2930 centimeter inverse. Okay, that means in between 29 to 3000. Okay, and when you have this kind of thing, double bond connected with this one, then this hydrogen frequency would be around 3100 centimeter inverse. Okay, and when you have this carbon hydrogen, then this carbon hydrogen frequency would be above 33 centimeter 100 inverse. And in the question itself it is given that 3314 centimeter inverse. It is clearly indicating that you should have in the question this carbon hydrogen connected with the triple bond. Okay, when it is connected with the triple bond, we can see the option. So in the option A, there is no such thing which is carbon single bond hydrogen. But if you don't have the idea about the IR spectroscopy, so you might get confused that SH is there. But please remember, this thionyl or this SH resonates around 2600 to 2550 centimeter inverse. So this A cannot be the answer. Okay, and in the option B, carbon triple bond nitrogen is there, and you know carbon triple bond nitrogen gives the staging frequency around 20 to 50. Again, this cannot be the answer. Now you looks for the option C. Yes, carbon triple bond carbon is there, carbon single bond hydrogen is there, right? So this actually gives this value, right? But in that case, carbon triple bond carbon is there, which correspond to 2126 centimeter inverse according to the question. Here again it will correspond to the 2126 centimeter inverse. So these two frequencies matches here, but this frequency is absent here, right? So option D can also be discarded. So option C is looking the correct answer in that case. So you can blindly mark the option C as the correct option. This is again a very simple or a straightforward problem. Now moving to the next problem, what it says, right? This problem is, guys, a little bit tricky, or sometimes it is difficult for the students who doesn't know the classes of the compounds or the kinds of the chirality. So for this I have made extensive lectures on the planar chirality or the chirality in the stereochemistry of the cyclophanes and your cyclic alkenes, right, and biphenyls. So this question only then if you have the idea about such a structure, only then you will be able to this question. You will be able to solve this question. Okay. So if you, however, if you haven't watched my video on this ENSA compounds, so this is basically the ENSA compound. What I can write here, the ENSA compound. ENSA compound, that means compounds, handle compounds basically, right? This is ENSA compound. Okay. So here is at the right top, you are having the link is blinking, and you can go through that link to understand the stereochemistry of the cyclophanes and ENSA compounds and all these things. Okay, guys. So you can see here, if I explain, see this is the compound, the handle compound, right? And here you see this is the plane of symmetry, right? This, see, if you forget about this one, CO2CH, right? Forget about this one, right? This is not there. Say for example, what I can do, I can immediately discard this. So right, I can use this one. Say this is not there, right? So in that case, you see this is the plane of symmetry. That means that plane of symmetry is here. That means this carbon and this carbon, this carbon and this carbon, they are of the same kind. So what I can do, I can mark them carbon 1, carbon 1, carbon 1, carbon 1. So all these 4 carbons will give you the one signal. Okay. And this is the carbon number 2. This is also the carbon number 2. They are the same. They are of the same kind, right? So I can write 2. I can write 2 here. I can write 2 here. Okay. Similarly, if this is 2, say this is 3. So of course this would be 3. There is no problem in that. Okay. So this is 2. What I can do here, say this is a 3. Okay. And this is the next one, which is the carbon 4. Okay. And again this is the carbon 2. Why? Because again you see the plane of symmetry is there. There is no question of this BR, these two BRs, because they are symmetrically placed here. They are actually in the symmetry plane. Okay. Symmetric structure. So this will not give disturb the stereochemistry of the structure actually, right? So in that case, you see how many, or if you see here, this is again 3, this is 4, this is 2, again this is for this one, this is 3, right? Opposite carbons are same basically, right? This and this would be same opposite carbons. This carbon and this carbon would be same. They are the opposite carbons. So what I can do, I can write 3 here, and this carbon and this carbon would be same. So I can write 4 here. And same is true for the lower half, because plane of symmetry is there. So only I am having the 4 different kinds of the carbon. So in the carbon NMR spectrum, I must get only 4 signals. But these questions can be solved only if you know the real concept about these compounds, or you can visualize these stereochemistry of these compounds. Only you will be able to solve this question. Otherwise, not. Okay. Now moving to the next problem, what it says that Proton NMR spectrum of an organic compound recorded on a 500 MHz machine showed a quadrate with the line positions at this, chemical shift and coupling constant of the quadrate are. Okay, chemical shift and the quadrate you have to chemical shift you have to calculate, and you have to calculate the coupling constant. So how you can solve this problem? Again, it's a very basic problem, right? See, quadrate according to the Pascal's triangle, this is the quadrate. Okay, this is the quadrate, and these values are given: 1741, 1747, 1753, 1759. Please remember, whenever you are writing these values, always this value actually, right, your right hand side value will come on the right hand side. This is 1741, and this one is 1747, and this one is 1753, and this one is 1759. And you know what is the coupling constant? Coupling constant is the distance in hertz between the splitted peaks. So you can take any of the distance, right? You can take this distance, this will give you the coupling constant. It is up to you. You can take this one, you can take this one, all will give you the same answer. You can do by yourself, but I am one actually I am showing you. I am going to calculate the J value is what? I am calculating this 1747 minus 1741. From this value I am subtracting the 1741 and I am getting the 6 hertz. Okay, so coupling constant is the 6 hertz. Straightforward problem. Now you can see the options. Coupling constant 6 hertz is given, so this may be the answer. But 12 hertz coupling constant, no, this cannot be your answer. You can immediately discard this one. And similarly 6 hertz, this could be the answer, but this 12 hertz cannot be your answer. You can immediately discard this one. So option B and option D, option B and option D, they are not actually your answer. They cannot be your answer. Option A and option C, you have to select between the option A and option C. So how we can solve this one? Say I am going to calculate the chemical shift. Okay, chemical shift in delta ppm. Okay, in the short way I am writing chemical shift is what? I can write shifts in hertz from TMS, okay, divided by spectrometer frequency, divided by spectrometer frequency, spectrometer frequency. Now you can see here how we can solve this one. So I can shift this little bit up. So screen is actually little bit distorted, but it will come again in the normal position. So how I can solve this question? Shift in hertz. So we have been given the 4 different shifts, right? First was I think 1759, and the difference of the 6 is 1753. Difference of the 6 is 1747. Difference of the 6 was 1746. Okay, right? And we can take the average of this one. Okay, so what I can do immediately, I can write divided by 4. Okay, and this is for this one actually. So this is not looking good. I can remove this. I can put my equal marks equality sign here. And what is the spectrophotometer frequency? It is the 500 megahertz. Okay, so if you solve this value, this will give you the 1750 in hertz divided by 500 megahertz. Okay, so I can move here actually, and if you solve this one, then it will give you here 3.5 ppm. Okay, so you know this is in megahertz, this is in hertz, so there is a concept of the 10 to the power 6 and 10 to the power minus 6, so you can get your answer actually. So I am straightforward solving this one. So 3.5 is the chemical shift and 6 hertz is the answer. So 3.5 and 6. So option A actually in that case is looking the correct option, so we can mark this one. Okay, now moving to the next problem, what it says. Again, this is December 2016 problem, and this problem, what it says, Okay, this question is basically from the theoretical NMR spectroscopy. If you have memorized the concept well, only then you will be able to solve this question. A static magnetic field is used to induce the transition between spin states. No, magnetic field is not used actually to induce the transition between alpha to beta, but radio frequency waves are used. So A cannot be your answer. You can discard this one. Okay. And what option B says? Magnetization vector is perpendicular to the applied magnetic field. No, it is not perpendicular. It is actually parallel to the magnetic field. Okay, again, this cannot be your answer. Now, what the option C says? Static magnetic field is used to create population difference between the spin states. Yes, definitely. This is the correct option. This option C is the correct option. You know, you have applied a particular magnetic field in the spinning nuclei, and that magnetic field actually will create the population difference. This is the basics. So option C is looking correct one, but we can check the last also. Static magnetic field induces spin coupling. No, spin coupling is not due to this magnetic field actually. So option C is correct one, right? Now moving to the next problem, what it says that. Another problem, number of lines in the fluorine-19 NMR spectrum of F2CBr, CBr, Cl2 at minus 20 degrees centigrade, assuming it is a mixture of static conformations given below. Okay. This is the first conformation of this compound. See, I have made a very extensive lecture series on the conformation and the conformational analysis, and I am again giving you the link at the right top and also giving you the link in the description box. You can go there and learn the concept from there if you don't know, right? If you know, then it is very good. So this is your first compound. Here you see one fluorine is here, another fluorine is here. This is chlorine, this is chlorine. So the chlorine of this environment of this fluorine is chlorine and Br. Environment of this fluorine is again chlorine and the Br. That means these two fluorines are of the same kind. So what I can write? I can write fluorine type 1, fluorine type 1. Okay. Now moving to the next problem. Now this is another conformation. Conformation, you know, if you rotate this one, right? If you rotate this one, right, then you will get this compound will get converted to another conformer. So you see again, this is the fluorine, which is having the environment of the bromine and the chlorine. Okay. And this fluorine, it is having the environment of the chlorine and the chlorine. That means this fluorine and this fluorine, they are not the same kind. They are not equivalent. Why? Because its environment is bromine and chlorine, and its environment is chlorine and chlorine. So they are the different kinds of the different kinds of the fluorine. So what I can do, I can mark them fluorine 1 and fluorine 2. Now looking at this one, right? So here you see the chlorine is reflecting here, fluorine is reflecting here. Basically they are mirror images. They are mirror images. If it is chiral, then it is enantiomer. Okay, right, like that you can see. Now if this fluorine is different, this fluorine is different, definitely this will reflect here also. This is type 2, this will be type 2 because this is the mirror image of this one, and of course this is type 1. So if you calculate the number of lines actually, splitting pattern or number of lines or the splitting, I can write. Formula is what? 2Ni plus 1. This is the formula. 2 is the constant, N is the number of the nuclei, types of the nuclei. So fluorine 1, only one type. So you can multiply it by 1. Multiply by I, right? This is the quantum number, which is half for the fluorine again. So you can write half here. This is plus 1. Okay, so 2 will get cancel out, and this will give you 2. So 2 lines you will get for this one, and here again you see for this one, again you calculate 2Ni plus 1. 2 is the constant, N is the number of the nuclei. So here this fluorine is different, this fluorine is different. That means 2 different kinds of the nuclei are there. So you can write 2 here. This is 1 by 2 plus 1. 2 will cancel out. 2 1s are 2 plus 1 3. So total 2 lines for this one and 3 lines for this one. And question itself says that they have recorded the NMR spectrum for this one, for this mixture actually. So how many lines would you expect? So if you have the mixture, then you will have total number of lines 2 plus 3 equals to 5. So 5 lines we can expect for this one, right? So option D is looking correct. So this is the correct answer for this one. Now moving to the next problem, what it says. Now again, this is my 2016 problem, right? So lecture is actually taking too much of time, but it is very important to solve all the problems, all the organic spectroscopy problems. Okay. Now this problem will take little time. Okay, this is not that easy problem. Okay. So the compound that exhibit the following spectral data, this is Proton NMR. Signal at 8.0, which is a doublet having the coupling constant of 12.3, and this is the one proton doublet. Please remember, it is a one proton doublet. 7.7, it is a doublet, 2 proton. 6.8, it is a doublet of 2 proton. Guys, this is the very important one. In the previous question I already told you, whenever you have the substituted benzene and you are getting 2 doublets of the 2 protons to different location, it shows the para-di substitution. It shows the para-di substitution. So if it is the para-di substitution, so this cannot be your answer, because this is ortho, right? And this is your ortho, this is meta. B cannot be your answer. You can immediately discard this one. But option C, this is, you see, this is ortho, this is meta, this is para. This could be the answer. Similarly, this is ortho, this is meta, this is para. So out of these two, option C and option D, anything could be your answer. Okay. So this is the trick actually which I am explaining you. So what I can do, I can immediately discard my wrong options. That means I can remove these two. Okay. Now we can go a little bit further. What it says that 3.0 signal of 6 protons. That means 6 protons means 2 methyls. 6 protons means simply 2 methyls. One CH3 and another CH3. So we have to look for the 2 CH3. Sorry guys, sorry for the delay, because in writing the question I actually made a mistake in writing the option C and option D. Now I have corrected these two options. We can go for the explanation of this one. Okay. Now we left with the option C and the option D. We have to select which one is the correct and which one is not. So what we can see here in that case, a very important feature which you can see here. This double bond can come here, this lone pair can come here, this can go up. And when you do this, this will have the resonating structure. This is your benzene ring, okay. And just like that, this is carbon single bond oxygen, okay. And here you see the double bond is like that, the nitrogen with positive charge. And this is your another CH3 and this is your another CH3, okay. Now you can see here this methyl and this oxygen, right? This methyl is the environment of this oxygen, while this methyl is not having this environment. That means these two are the different kind of the hydrogens. When these two are of the different kind of the methyl hydrogens, like these two methyls are the different, they cannot give you the signals, one signal. It will produce one signal, it will produce another signal. That means we should have the 2 singlets of the different chemical shift. But question is showing only 1 singlet of the 6 proton. But this option cannot give you the 1 singlet of the 6 proton. So option D cannot be your answer. You can immediately discard option D also. What you left with the option C. Option C is actually looking the more correct option. So if you want to solve the NMR of this one, say this is hydrogen which is here, this is hydrogen which is here, okay. Now these two will give you a 6 proton singlet at 3.0 ppm, okay, which is this one. There is no problem in that, okay. And then you are having say this hydrogen, right, which is in the environment of the carbonyl, and this hydrogen which is having the environment of the phenyl, okay. So obviously due to this carbonyl group, actually this is the de-shielded one. When it is de-shielded one, so it will have it will have the higher chemical shift, that is 8.0 ppm, and this will have lower chemical shift at 5.8 ppm. And since they are the transly substituted, so trans coupling would be there. when the transcoupling would be there, so you know the transcoupling constant, which is 12.3 here. Transcoupling is happening here in that case. Okay, and similarly 8.0, you see the this signal at this 8.0. This is the coupling constant, sorry. Okay, so this is how, no sorry, J value is this one, 6.8, 7.7. okay, so I made a mistake actually, right? So this is 5 point, this is not 5.8, yes, this is 5.8. okay, and this is 6.8, this one. Okay, and rest thing, you know, this benzene you can go like that, right? These two kind paradise substitution, so they are of the same kind. So option C is looking the more correct option in that case. Okay, now moving to the next problem, and I hope this is my last problem. Okay, so this is the last problem of 2016 question paper. In the 200 megahertz NMR spectrometer, a molecule shows two doublets separated by 2 ppm. That means the difference in the chemical. See, separated by the 2 ppm, you can convert it into the hertz also very easily. The observed coupling constant is 10 hertz. The separation between the two signals and the coupling constant in 600 megahertz machine would be. Okay, what it says that first for the same molecule, first we recorded the spectrum at 200 megahertz machine, and after we have recorded the spectrum at the 600 megahertz machine. Now what would be the new coupling constant and the separation between the hertz, separation between the two signals. Okay, but please remember from the basics of NMR spectroscopy, coupling constant never changes. That's why its name is constant. So if the first coupling constant, if my first coupling constant is 10 hertz, then in the new spectrometer also I must have the first coupling constant of the 10 hertz. So here you see the coupling constant is 30 hertz, cannot be your answer. Okay, coupling constant of the 30 hertz cannot be your answer. This is the coupling constant of 10 hertz, yes, this could be the answer. Coupling constant of 10 hertz, yes, this could be the answer. Now there is a competition between the C and D. Now this again is very easy. This is very easy, you should know, right? See, generally what happens in that case, you can immediately write the chemical shift formula. Delta ppm, what it says that the shifts in hertz from tetramethylsilane divided by spectrometer frequency in megahertz. Spectrometer frequency in megahertz. Okay, so this delta ppm is given here, 2 ppm, the difference of the 2 ppm, this is given here, so you can write 2 here, and this shift in hertz you have to actually calculate it. Okay, so what I can write here, I can write delta hertz. However, this is not the way of writing, I am writing the delta hertz. Okay, and this should be divided by the spectrometer frequency. New spectrometer frequency is 600. So this will give you one shift in hertz, that is delta z at z, 600 into 2, that is 1200. Okay, so where is that? Yes, option D. So in that case option D is looking the correct option. So these are the simple problems which you can solve, right? I hope you enjoy the lecture and you understood the problems pretty well. Even after completing this lecture, if you have any doubt in any of the problem, you can comment in the comment section. Okay, I'll try to reply your queries with the best of my capability. So that's it for today from the Tetrahedron Chemistry classes. If you are new here and watching video for the first time, please subscribe the Tetrahedron Chemistry classes. Do share with your friends also, guys. Okay, so that's it for today. We'll meet in the next lecture with the 2017 problems. Thank you very much.